that I wrote up nice and neat. These problems are so long and complicated. Like if I'm watching something like this, I know I've mentioned this several times. I think I learn better when all the stuff appears in front of me as the professor is saying it. I have a hard time following along when somebody's reading math to me. I would rather watch somebody write it out. The problem is these problems are so bad. If I were to just write this out in front of you, there's a good chance I'm going to mess up somewhere. And I don't want that. So I wrote these out to make sure they're 100% correct before I go through them. I guess I could print it out and have it beside me and rewrite it in front of you. But okay, here's our DE. Okay, so we're going to find the power series solution here. And this is what's going to mess us up right here, having this x squared and this x here. That's going to make it impossible to get all of our powers and our starting point for indices to match up. And we're going to have to break off a couple of extra terms. Okay, and we'll see right there, it's both of these guys will cause a problem. Okay, so we start with our general assumption, just like always. We assume y can be written as an infinite power series. We take the derivative. Now, I know because I've done the problem. Remember, with this derivative power series here, so I just took the derivative here. It's just power rule, right? N comes down, drops down by 1. The first term, when I plug in n equals 0 here, 0 times anything is 0. I could, if I wanted to, say, well, the first term 0, I'm going to start that at 1. But because we've got this x squared there, I'm not going to do that. And same thing, well, I won't have that issue here. Okay, we take the second derivative. We get this, same thing we get every time. And then for the reasons I was just saying, the n equals 0 term is 0, the n equals 1 term is 0. I can just ignore both of those and say, well, we really start at 2. So these two literally say the same thing because the first two were 0. Now, maybe I don't want to do this. Maybe I do. We never know. You really just got to get in and play with each one. But I definitely don't want to have an n minus 2 in here. So I want this to be n. So I need this to go up by 2. So everything inside the sum, all the n's are going to raise by 2. So that becomes n plus 2. That n becomes n plus 2. N minus 1 plus 2 goes up to n plus 1. Everything here went up by 2. So that I'm not changing anything. The way I counteract that is I drop this guy down by 2. So it looks like magic. It looks like if you look from here to here, I just changed everything inside the sum. But I was only able to do that because those first two terms were 0. So I really had to make this intermediate step. Then I could play that game. Okay, so notice here, I did not play that game with this guy. So I've got this x squared out in front of the y prime. So that's going to distribute in across this infinite sum. We're only allowed to do that because we're assuming the sum converges, by the way. N minus 2 plus 2 more would be an n plus 1 here. And same game here. I've got this extra x out front here. So x to the n times 1 more x will be an n plus 1. And I brought that 2 in. So now I need all 3 of these indices to match up. They all have to have the same power and they have to all start at the same point. Otherwise, I can't squish them together. That's your main goal in a power series. Make all the powers the same, make all the starting points the same. Okay, so these guys are all n+1. I need this guy to go up by one more. The problem is I can't do that. That game I played right here, where I raise these up and then drop this down, I can't have negative starting points. So if I were to raise all these up by one, I would have an n equals -1 here to counteract that. I can't do that. There's no way to raise this up and make it match. So what I have to do is make everybody start at 1. I need to get rid of that first term. So I'm going to find the n equals 0 term. Okay, so this first guy, I'm just dealing with just this first guy. If I plug in an n equals 0 into him, so I'm plugging in into all the n's, n equals 0. So 0 plus 2, a2, 0 plus 2, 0 plus 1, x to the 0. These two guys I haven't done anything with. Have I? Let's see. What did I do here? Oh, yeah. So I plug in 0 to this guy. His first term is 0 because of that n right there. That's a sub n times n. So his first term was 0. And then I'm not doing anything with this guy. Okay, so this guy has an x to the 0. These two guys won't have an x to the 0. So really what I'm figuring out is the x to the 0 term. So this whole thing is supposed to equal 0. That means, remember, when we're solving for the coefficients of a power series, we're setting every single coefficient equal to the coefficient it has over here. Over on the right, this is 0 plus 0 x to the first plus 0 x squared plus 0. These are all zeros. So this junk right here, then, the x to the 0 I get on the left side must be 0 x to the 0 on the right. From that, I can solve for a sub 2 and get a2 equals 0. Okay, so what did I do there? I took care of this n equals 0 term in this guy. I don't have to worry about that anymore. Now let's worry about all the rest of them. Now I can bump this up to a 1 because I already took care of the x to the 0 term. If I make this a 1, now I can play that game where I raise this up by 1 and drop that down by 1. Now I have room. I've got the space to drop this starting point down by 1. So we're going to raise all these up by 1 and drop that one down by 1. That way all the powers will be n+1, and all my starting points I'm going to have to match up. So that's where this came from. This really was now n equals 1. Raised all those up 1, dropped that down by 1. Now look at all my powers, n+1, all my starting points, 0. I got to keep this in mind, though. From that one I broke off, a2 equals 0. Okay, now that all my sums look identical, I can squish them all together into one single sum. The only way all of this can equal 0 is if that coefficient, all this stuff here inside the brackets, equals 0. And I get this recursive formula. So I end up with a n plus 3 depending on a n. So where did a plus 3 come from? Remember, here we raised all these up by 1 to drop that down by 1. So I get a plus 3 there, I get a plus 3 there. Okay, so I just did some algebra here, clean that up a little bit, and we get this. These n plus 2's cancel. Here's our recursive formula. So second order power series, we're always, every single time, going to have A0 and A1 will be free. Every time. If it's a second order differential equation, the first two are going to be free parameters. Our recursive formula, the stuff we get from all this junk up here, will tell us all the rest of them in terms of those two. That one we broke off told us A2 will be 0. Okay, so I'm using this formula. If I plug in n equals 0, so 0 plus 3 is A3. I get A0 over 3. I'll do a couple of these here. If I plug in n equals 1 into this formula, A4, plugging in a 1 there, plugging in a 1 there, we get this. What about if I plug in an n equals 2? We get A5 is the opposite of A2 over 5, but wait a minute, A2 was 0. So that'll make A5 0. And we just keep going. And every third one here is going to be 0. Remember, the powers of x match up, not here. These do not give you, excuse me. The ends don't tell you the power of x, the subscript. A3 goes with x cubed. A7 goes with x to the 7th. The subscript on the A goes with the power of x. So here is A2 was 0. That's why we don't have an x cubed. A3 was this thing right here. That goes with x cubed. See, here's A4. That goes with x to the 4th. Notice there's no x to the 5th because A5 was 0, and so forth. So that's the full solution. And sometimes the question will ask you just for the full solution and you're done, you stop there. Other times the question will ask you to split it up into two pieces, the parts with the A0s and the parts with the A1s. So the A0s, I've put those all together here, like literally just writing some of them down. Here are the A1s. And I don't know who came up with this numbering convention. This is weird. Y here is Y1 plus Y2, where Y1 is all the A0 stuff and Y2 is all the A1 stuff. I hate that 1 goes with 0 and 2 goes with 1, but somebody decided that, and that's the way we all kind of write it up. Okay, so this is all written out nice and pretty. Hopefully it's all legible. Let's do another really hard one like that. Did I just click the same one twice? I think I did. Another hard one. Here we go. I was looking at it thinking that looks exactly the same. Okay, so now we made it even worse. See, ideally, what we would like to have in a perfect world, no x's here, one x here, and then if we put any x's here, we have a singular point. So we could do like maybe 1 plus x squared here, so that we wouldn't have any singular points. X squareds, x, no x's, then all my powers just line up and I'm done. It's so easy. Adding in extra x's here makes things worse because now it's really hard to make this guy match that guy. And we'll see that. So we start with the assumption that y is an infinite power series. I call that equation 0. Here's my derivative. And I played the normal game of, well, the first term is 0, so I might as well start at 1. And then let's make these x to the n. So let's raise everything here up by 1. We counteract that by dropping this starting point down by 1. Okay, here's my second derivative. Same thing we always get. And same game there. First two terms are 0, n equals 0, makes this 0, n equals 1, makes this 0. And then I can raise all these guys up by 2 to make that x to the n, drop this guy down by 2, and I start at 0. So now if we put all this together, we've got this 5x squared there that's going to cause an issue. So here is what I'm assuming y looks like. X to the n plus 2 more x's will be n plus 2. So everybody here I got starting at 0. I've got here an n plus 2. These only have a power of n. I need all of those to match. So I would like to raise this up by 2 and drop that down by 2. I can't. I can't have negative starting points. So what we have to do is break off the first two terms. Plug in n equals 0 and n equals 1 so that I have the space. Deal with those two terms by themselves. The x to the 0 and the x to the 1 terms by themselves. Okay, so the x to the 0. Remember, I'm thinking about my power here, not necessarily the value of n. I'm thinking x to the 0 power. This guy doesn't have any x to the 0 powers. These two do. If I plug in n equals 0, so plug in n equals 0 everywhere here and here. That gives me this equation. Plug in n equals 1. Okay, so I guess I'm trying to figure out what I did here. I did both simultaneously. Plugged in n equals 0. That's this. For all my n's, plug in n equals 1 to both of these for all my n's. That's supposed to equal, what do we have on the right? 0. I'm supposed to have a 0 x to the 0 and a 0 x to the first. So this thing here must be 0. That gives me a2 equals negative a1. This thing here, from here to here, must equal 0x to the first. That gives me a3 equals 2/3 a1. So if I had had an x to the 7th here, I would have had to do this 7 times, break off the first 7 terms up to x to the 6th. Now, since I already dealt with the 0 and the 1 term, I don't even care about those first 2 terms anymore. I could start both of these guys now at 2. So here's, I called it star. Let's starting at 2 now, because I already dealt with the x to the 0 and x to the first. Now I've got the space, because I've got a 2 here. I can drop this down by 2, allowing me to raise everything else up by 2. Same game, like literally the same game here. Then I put all that together into one single sum. Now everybody has an n plus 2. Everybody starts at 0. So I can squish this all together, combine all of my coefficients. That must equal 0. And I get this really nasty recursive formula. So an plus 4 here depends on an and an plus 3. So to second order, I'm always going to have two free parameters here, a0 and a1. Everything else will depend on those two. And then I found these by breaking off those first two terms. Here's my recursive formula for everybody else. That's going to start when I plug in n equals 0 here. That's going to give me a4. Okay, so just for my own convenience, I rewrote that. And just start plugging in n's here. Plug in n equals 0 for every n I see. And like, I don't even get something pretty because this depends on two different terms. I get this a0 times a1, all this nasty stuff here. Plug in an n equals 1 here. I get, there's going to be an a1 in there and an a4. But I know what a4 is. It was all this. So I have to go backwards and plug all that in. Remember, I want everybody in terms of 0 and 1, a0 and a1. Like, and then there's just a whole bunch of arithmetic. I'm not going to bore you going through it step by step. But I'm simplifying each of these in terms of a0 and a1. So you can check all these details on your own. And then I got bored with writing all this out. I just stopped there and said, that's good enough. So this was my A2 right here, my A3, my A4 was that. Here's A5 that I just found. And like literally, if I were to give you a problem like this, we would be done. We would not even try to separate these out into the Y1 and the Y2. Like, look how nasty this is already. But I went ahead and did it here just for completeness. I would never, I don't know that I would give you a problem this bad. And if I did, I definitely would not ask you to separate these out. You could just stop there. But I went ahead and separated them out. I found everything here that had an A0 in it and everything that had an A1 and squished them into their appropriate pieces.